Dear students, now today we start part 2 of conformal mapping, and we start with this part with the analytic function. Analytic functions and conformality. In it we have a theorem: if f such that u approach to C is analytic and if z0 belongs to u such that f dash 0 is not equal to 0, then f is conformal at z0. We have a proof in a proper manner. Suppose gamma such that closed interval a comma b tends to u is a curve in u with gamma of t0 is equal to 0 for some t0 belongs to open interval a comma b, then f o gamma with transpose of t0 is equal to f dash of gamma of t0 into gamma dash of t0 is equal to f dash z0 gamma dash t0. So f o gamma dash t0 is obtained from gamma dash t0 via multiplication by f dash of z0 equal to rotation and stretching. If gamma 1 and gamma 2 are two curves in u through z0 with tangent vectors gamma dash of t1 and gamma dash of t2, then f o gamma dash of t0 and f o gamma dash t0 are both obtained from gamma dash t1 and gamma dash t2. At here we have some point t0 and another one is t0 in the sense of t1 and t2 respectively via multiplication by f dash z0. The angle between them is thus preserved. Now we have example. We consider the mapping w is equal to e raised to z in the complex plane. Since w equal to f of z, the derivative f dash of z0 is equal to e raised to z, which is not equal to 0 for each z. Thus, if it is a conformal map throughout the entire z plane. Another example, we have the function f of z is equal to z square plus z plus 1 is conformal except z equal to minus half, since it is analytic everywhere and f dash at minus half is equal to 0. Now we are going to define a critical point. If f is analytic at z0 and f dash of z0 is equal to 0, then the point z0 is called a critical point of f. We have example on it. The function f of z is equal to sin z is analytic everywhere and hence represents a conformal mapping except at the critical points z equal to 2n plus 1 pi by 2, where the derivative f dash z vanishes. Now, the behavior of an analytic function in a neighborhood of critical point is given by the following theorem. Theorem is as follows: let small f be analytic at z0 and if f dash of z0 is equal to so on and is equal to f z0 with derivative of the level k minus 1 and f of z0 derivative of level k not equal to 0, then the mapping w equal to f of z magnifies the angle at the vertex z0 by a factor k. Now we have example. Find the image of the unit square S is equal to x plus iota y such that x lie from 0 to 1 and y lie from 0 to 1 under the map w is equal to f of z is equal to z square. So for solution we may understand in such a way the map f of z is conformal at all z not equal to 0. So the vertices z1 equal to 1, z2 equal to 1 plus iota and z3 equal to iota are mapped onto right angles at the vertices w1 equal to 1 and w2 equal to 2 iota, and last one w3 is equal to minus 1. But f double dash of z of 0 is equal to 2, which is not equal to 0. So the angle at the vertex z equal to 0 is magnified by the factor 2. Now another example is here. Show that mapping w equal to f of z is equal to cos z is conformal at the points z1 equal to iota, z2 equal to 1, z3 equal to pi plus iota, and determine the angle of rotation argument f dash z at the given points. So for solution we have, since f dash z is equal to minus sin z, the mapping w is equal to f of z is equal to cos of z is conformal at all points except z equal to n pi, where n is an integer. Therefore f dash at iota is equal to minus sin iota, and the conversion in the hyperbolic function we have this result is equal to minus iota sin hyperbolic 1, and f dash 1 equal to minus sin 1 and f dash pi plus iota equal to minus sin pi plus iota, that is after simplification we have is equal to iota sin hyperbolic 1. Thus the respective angles of the rotation are given by argument f dash iota equal to minus pi by 2, argument f dash 1 is equal to pi, and argument f dash pi plus iota is equal to pi by 2. These are the results. Now we have a sufficient condition for w equal to f of z to represent a conformal mapping. For it we have a statement of the theorem. As a result, let f of z be an analytic function of z in a region D of the z plane, and let f dash z not equal to 0 inside D, then the mapping w equal to f of z is conformal at the point D. Necessary condition for w equal to f of z to represent a conformal mapping, we have the theorem for it. If the mapping w equal to f of z is conformal, then the function f of z is an analytic function of z. These are two results as a part of theorem in the sense for sufficient condition as well as necessary condition to represent a conformal mapping. Now we have observed that using conformal maps, harmonic and analytic functions defined in the domain with difficult geometry can be studied in the domain with simple geometry. Riemann mapping theorem establishes the existence of such a conformal map that maps arbitrary domain simply connected and bounded to unit disk through, though it doesn't explain the way to do this. Thus, in this theorem is of extreme importance. So, the theorem of Riemann for mapping purpose, we have Riemann mapping theorem. The statement of the theorem is, if D is a simply connected domain, that is open connected, no holes, such kind of known as connected domain, in the complex plane but not entire complex plane, there is conformal map, that is analytic 1 to 1 and on to of the D into the open unit disk. So we have a diagram. In it we have a different shape of curve. Point Z0, domain D tends to same special type of circle where f of Z0 is equal to 0 and the domain. So we may say that D is conformally equivalent to D. So here we have a definition of bilinear transformation. It's another part and very useful for numerical kind of questions in examination. A bilinear transformation, also called fractional linear transformation or Mobius transformation, is a function of the form w is equal to f of z is equal to az plus b upon cz plus d, where a, b, c, d all belongs to complex number c, and determinant of a, b, c, d is equal to ad minus bc, that is not equal to 0. Now we have an important point to mark here. F dash z is equal to cz plus d with za minus az plus b multiplication with c upon cz plus d whole square. So we have ad minus bc upon cz plus d whole square. The condition ad minus bc not equal to 0 thus simply guarantees that f is non-constant and conformal. We have another remark. If we multiply each of the parameter a, b, c, d by a constant k not equal to 0, we obtain the same mapping. Hence, a given mapping does not uniquely determine a, b, c, d. It's a very important result and very interesting result. Now we are going to understand some results for bilinear transformations. Following observations can be made regarding bilinear transformations. Number 1, as z approach to infinity, f of z approach to a by c if c not equal to 0, and f of z approach to infinity if c equal to 0. Similarly, f at minus d by c is equal to infinity if c not equal to 0. We thus regard f as a mapping from the extended complex plane c cap is equal to c union infinity to the extended plane c cap. The real line has two infinities, plus infinity and minus infinity, but complex plane has only one infinity, defined as north pole on the Riemann sphere in stereographic projection. Extended complex plane is denoted by c cap is equal to c union infinite. It's very interesting result. We must notice this one. Now, Mobius transformation are the only conformal mapping from C to C. If C equal to 0, comma d equal to 1, then f of z is equal to az plus b, comma a not equal to 0 are also called affine transformations. They map infinity to infinity and therefore map C to C. In fact, these are the only conformal mappings from C to C. In particular, if f of z equal to az, comma b equal to 0 is the rotation and dilation, then we have f of z equal to z plus b, where a equal to 1 is the translation. And second point is a equal to 0, b equal to 1, c equal to 1, d equal to 0, then f of z equal to 1 by z. This is an inversion f interchange outside and inside of the unit circle. So these are some observations on the behalf of conformal mapping for Mobius transformation. Now we have some result for bilinear transformation as known as properties. A Mobius transformation is one to one and onto from C cap to C. And another result, every bilinear transformation of a circle or a straight line is again a circle or a straight line. Another result, if A, B are inverse point for a circle gamma and A dash, B dash and gamma dash are bilinear transformations of A, B and gamma, then A dash and B dash are also inverse points for gamma dash. It is a very important result, so we must notify these results. And further, after this discussion, for next lecture we will continue with fixed point as well as some properties. So we will continue later. Thank you.